So in this section, we're going to kind of put these covalent bonding ideas together. And we're going to draw the Lewis structure of three things: SO3, ClO2 minus, and CH5N. We're going to find the Lewis structure, the electron geometry, the molecular geometry. We're going to determine if it's polar or nonpolar. We're going to find the hybrids used for all the unique atoms. We're going to find energetically equivalent resonance and the total sigma and pi bonds. So how many sigma and pi bonds there are in the best Lewis structure. So we have quite a bit of work to do here. But the important thing to remember is that once we draw the Lewis structure, we can essentially determine all these other things from the Lewis structure. But everything starts with the Lewis structure. So when you see SO3, for example, you can't simply just look at SO3 and be like, oh, I know the electron geometry. You have to first draw the Lewis structure. And that's very, very important. So let's take a look at actually doing this. So we have SO3. So we use our periodic table. We find that sulfur has 6 valence electrons. It's in 6a. And each oxygen has 6 valence electrons. There's 3 of them. So we have 6 times plus 3 times 6, which is equal to 24 electrons. So SO3, I'm going to rewrite this so it's a little bit bigger. SO3 is 24 electrons in total. So we counted the valence electrons. Now we're going to put the least electronegative atom in the middle, S, and bond it to 3 oxygens. If I put 8 electrons around each oxygen, I have used all 24 electrons. So putting 8 electrons around each oxygen is a total of 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, because 3 8s are 24. So when I look at this Lewis structure, before I calculate the formal charges, I need to see if essentially we have a full octet. And when I look at this, I realize I don't have a full octet. So what I'm going to do is, because I'm realizing I'm going to run out of space, I'm going to rewrite this over on this piece of paper. So I have S bond O like this. And I'll move this down in 1 second. So I just rewrote what I had before. I just wrote it where I have a little bit more space. So this Lewis structure uses all 24 electrons, but it's not ideal because I have not filled the octet of sulfur, so let's fix that. So I move those 2 electrons there, and what I get is S double bond O, like so, bond O, bond O, like that. And what I notice here is that I have now an octet on everything. There's 2, 4, 6, 8 electrons around oxygen, 8 around sulfur, and 8 around these oxygens. So now I can calculate the formal charges. So I'm going to start with the oxygen. So oxygen wants to have 6 electrons around it. Count the dots as 1, count the dashes as 1. This one has 1, 2, 3, 4, 5, 6, 7. It has an extra electron, so it's negatively charged. This sulfur wants to have, or excuse me, this oxygen is the same. 1, 2, 3, 4, 5, 6, 7. So it's negatively charged. How about this oxygen? This oxygen has 1, 2, 3, 4, 5, 6. It wants 6, it has 6, it's neutral. How about sulfur? Sulfur wants to have 6 electrons around it. It has 1, 2, 3, 4. It's missing 2 electrons, so it's positive 2 as its charge. Now, as I look at this Lewis structure, I'm noticing these formal charges aren't very good, right? I want to make them all 0 if at all possible. So the way I can minimize the formal charge here is by moving these 2 electrons here. That'll take an electron away from oxygen and add 1 to sulfur. And I'm going to want to do that twice. However, before I can do that, I want to ask myself, can sulfur expand its octet? And when I look here, I find that sulfur is in period 3. Remember that atoms period 3 or lower on the periodic table can expand their octets. So I want to expand sulfur's octet. So I want to move these 2 electrons here and these 2 electrons here. Notice I'm not starting over in any case. I'm just moving electrons. And what I end up with is this as my Lewis structure. Now this is a better Lewis structure because all the formal charges are now 0. So what I'm going to do is just copy that one onto my paper over here because I realized I was going to run out of room if I tried to do all that stuff I just did on this little box, in this little box. So now I have my best Lewis structure like so. Now I want to find the electron geometry. Well, how do I find the electron geometry with respect to the central atom, sulfur? I find the electron geometry by counting the domains. There are 1, 2, 3 domains. So the electron geometry always comes out of the first column. So there are 3 domains. The electron geometry for 2, 3 domains is trigonal planar. So the answer here is trigonal planar. The molecular geometry. Well, since none of these domains are lone pairs, the electron geometry and the molecular geometry are the same. So this is for 0 lone pairs. So the electron geometry and the molecular geometry are the same. This is also trigonal planar. Polar or nonpolar. In order to determine if something is polar or nonpolar, I want to see if all the domains are the same. In this case, oxygen, oxygen, oxygen. So all of the domains are oxygen. There's no lone pairs or anything like that. So this is non-polar. Hybrids used, and I want all unique atoms. In this case, all the oxygens are the same. So we have sulfur and we have oxygen. So to count for hybrids, we want to count the domains because the domains, which contain lone pairs and sigma bonds, are also the same thing that count for hybrid orbitals. So we have sulfur 1, 2, 3 domains. That means we have 3 hybrid orbitals. S, P, P. 1, 2, 3. SPP. We abbreviate that SP2. For oxygen, how many domains we have? They're all the same. 1, 2, 3. The 2 lone pairs and the sulfur. SPP. 1, 2, 3. We abbreviate that as SP2. Energetically equivalent resonance. Does this molecule have a double bond that can be in another place? This molecule does not have a double bond that can be in another place, so the answer here is no. If we look back to here, this and the example with one double bond and one single bond and 2 double bonds would be minor resonance forms because they're less stable. So it does have resonance, but it doesn't have any energetically equivalent resonance, which we're asked for here. Now we need to do total sigma and pi bonds. First, let's count all the bonds. 1, 2, 3, 4, 5, 6. So we have 6 bonds that we want to identify. How many of them are sigma? 1, 2, 3. The first bond of a double bond is a sigma. How about a pi? 1, 2, 3. The second bond of every double bond is a pi. So it has 6 bonds, 3 are sigma, and 3 are pi. So notice, once we draw the proper Lewis structure, we can figure out all this other information about it that we've learned in these chapters. Let's do another example. Let's do ClO2 minus. So this is ClO2 minus, so it's a little easier to see. So what we have here is 7 plus 2 times 6 plus 1 because it's negatively charged. So we have 12 plus 12 plus 7, which is 19, plus 1, which is 20 electrons. All right, this is the chlorite ion. So we want to put the least electronegative in the atom in the middle. I'm going to draw it over here. So we have Cl in the middle, and we're going to bond it to 2 oxygens, and we're going to put 8 electrons total around each oxygen, so we can count by 8s. So we have 20 electrons to place. If I have 8 electrons around this oxygen and 8 electrons around this oxygen, I have used a total of 16 electrons. If I have 20 electrons total, I need 4 more electrons. And that is 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Just to double count them. Now, I ask myself, have I filled the octets? And the answer is yes, I have filled the octets. Now I want to calculate formal charges. So, in this case, the formal charges are oxygen wants to have 6 electrons around it. How many does it have? 1, 2, 3, 4, 5, 6, 7. It's negatively charged. This oxygen is the same, so it's also negatively charged. Let's look at chlorine. 1, 2, 3, 4, 5, 6. It is missing an electron because it wants to have 7 and it only has 6, so it's positively charged. Notice that the sum of the formal charges has to be the sum of the charge of the species. That means you counted the electrons properly. So minus, 2 minuses and a plus add up to a minus, so we're good to go. The question becomes, rule 4 is not calculate the formal charges, it's minimize the formal charges. Well, how can I minimize the formal charges? How I can minimize the formal charges is by moving electrons. So if I were to move these electrons here, I would make this a 0 and this is 0 because I would take essentially an electron away from oxygen and put that electron onto chlorine. The question is, can chlorine expand its octet? And chlorine is in period 3, so it can expand its octet. So I'm going to move those electrons. And when I do, I get Cl double bond O. I'll draw them this way. Yeah. Gotta be more careful here. I'm going to put it down here. Cl double bond O. I just wanted to show those actual electrons moving over. And bonded to O over here. And Cl kept its 2 lone pairs. So this Cl is minus, and this Cl is now neutral because I add an electron to it by adding a bond. If you're not sure, just count it again. It wants to have 7 around it, has 1, 2, 3, 4, 5, 6, 7. It's neutral. Oxygen wants to have 6 and it has 1, 2, 3, 4, 5, 6. It was minus, we moved an electron away from it essentially, so we end up with this. Well, you might ask yourself, what about symmetry? What if we do that one more time? What if I move these 2 electrons here? If I did that, I'd end up with Cl, keeps its lone pairs, double bond O, double bond O. And in this case, I now move this minus charge from here on oxygen. I take an electron away from oxygen and I add an electron onto chlorine, so I give it a minus charge. If you're not sure, just recount it. Chlorine 1,7 has 1, 2, 3, 4, 5, 6, 7, 8. So it wants 7 and it has 8. So I think it's clear that this one or this one is probably better than this one because they have less formal charges. In this case, all the atoms have formal charges. In these cases, only one of the atoms has a formal charge. Now it's arguable whether this case or this case is better, I don't know. But this case is the best. Why is this case the best? Because the negative formal charge is on oxygen. Why is that good? Because oxygen is the more electronegative atom. This is a tough one because oxygen and chlorine are equidistant from fluorine. But one thing to remember is oxygen is more electronegative than chlorine. Oxygen is 3.5 and chlorine is 3. So even though they're equidistant from fluorine, oxygen is more electronegative. So this is basically the one you want. Also note, oxygen is not the central atom. The least electronegative atom goes in the middle. So chlorine is in the middle. So this is our Lewis structure. So I'm going to just copy that over here on this paper, like so. And this oxygen is minus, and everything else is neutral. All right, now that we've drawn the Lewis structure, we want to find the electron geometry. Well, the electron geometry is based on the domains. How many domains do we have with respect to chlorine? 1, 2 lone pairs, and 2, 3, 4, 2 oxygens. So a total of 1, 2, 3, 4. So this has 4 domains. Remember, your electron geometry always comes out of the first column. So 4 domains out of the first column is tetrahedral. Now we want to look at of these 4 domains, 2 of them are lone pairs. So we have 4 domains, 1, 2, 3, 4, 2 of which are lone pairs. So we go to 4 domains, 1, 2 lone pairs, 2 lone pairs, 4 domains, and we find that this is bent. Next question, polar or nonpolar? Well, are all the domains the same? No, 2 of the domains are oxygen and 2 of the domains are lone pairs, so we're going to call this one polar. Hybrids used. Now, because this molecule exhibits resonance, it's really a 1.5 bond on this side and a 1.5 bond on this side. So this does have energetically equivalent resonance because this double bond could be here or this double bond could be here, and it's 1.5. And that could confuse the hybrid used situation. So we're going to find the hybrid used for practice based on the Lewis structure that's drawn on the paper. But it's just for practice. In real life, we do have this hybridization thing going on. So I'm going to label this as oxygen A, and this is oxygen B. So the single bonded oxygen is oxygen A, and the double bonded oxygen is oxygen B, just because I wanted to label them as A as B. If you want 1 and 2, it doesn't matter. So we have the chlorine, OA, and OB. And we want to look at the hybrids used. Again, we're doing it for as written on the piece of paper. We're kind of ignoring the resonance. So here we have for oxygen A, how many domains? 1, 2, 3, 4. 4 domains means S, P, P, P. 4 hybrid orbitals, sp3. For oxygen B, we have chlorine, lone pair, 3 domains, spp, sp2. And for chlorine, we have 1, 2 lone pairs and 1, 2 oxygens for a total of 1, 2, 3, 4 domains, spp, sp3. Now we want to find sigma and pi bonds. Well, how many total bonds do we have? 1, 2, 3. So we have 3 bonds that we need to identify. And in this case, we want to find how many are sigma and how many are pi. So there is 1 sigma and 2 pi. Excuse me, 1, 2 sigma, and the second bond of the double bond is the pi. So the single bond is a sigma, and the double bond is a sigma and a pi. So that's a total of 1, 2 sigma and 1 pi. All right, last example. The last example is a little bit complicated because it has multiple central atoms. So in this case, we have CH5N. So this is CH5N. When we do this, we want to count the electrons. 4 plus 5 times 1 for hydrogen plus 5 for nitrogen for a total of 14 electrons. So this has a lot of atoms, but not very many electrons. So let's look at CH5N, and it's 14 electrons. So if I draw carbon in the middle, and I draw 1, 2, 3, 4, 5 H's around it, and an N, you're instantly going to say, well, that's not going to work. And how do you know that's not going to work? Well, you know that's not going to work because carbon is a period 2 element, which cannot expand its octet. This Lewis structure massively expands carbon's octet. So we know that there are multiple central atoms. So we have to have a second central atom. We're going to take carbon and nitrogen and make them both central atoms. And the reason that we're taking carbon and nitrogen as both central atoms is because hydrogen can't be a central atom. So we know that carbon and nitrogen have to be the central atoms. Now we want to put the appropriate number of hydrogens around each one. So what I'm going to do is I'm going to put 1, 2, 3 hydrogens around carbon to fill its octet. And now I have 2 more hydrogens. So I'm going to put those other 2 hydrogens around nitrogen. Now I'm going to count the electrons. 2, 4, 6, 8, 10, 12. I've only used 12 electrons. That's good because nitrogen doesn't have an octet. So I want to put that lone pair on nitrogen. Now, you may have chosen to do this. 1, 2, 3 hydrogens around nitrogen, and then 1, 2, the other 2 hydrogens for a total of 5 around carbon, and then put the lone pair on carbon. Let's figure out which of these two structures is better. And the way we're going to figure that out is formal charges. So carbon likes to have 4 electrons around it. In this case, it has 1, 2, 3, 4. Count the dots as 1, count the dashes as 1. So this wants 4, has 4, it's neutral. Nitrogen likes to have 5 electrons around it. Count the dots and dashes as 1, 1, 2, 3, 4, 5. It's also neutral. In this case, carbon still likes to have 4, and it has 1, 2, 3, 4, 5. So it's minus. And nitrogen likes to have 5, and it has 1, 2, 3, 4. So it's plus. This is the best Lewis structure because it has minimal formal charges. In fact, they're all 0. This molecule is called methylamine. If you've ever seen the show Breaking Bad, this is one of the molecules that they were interested in because they were turning it into methamphetamine. So let's draw our best Lewis structure over on this paper. So we have CH, H, H, bond N, lone pair, and 2 H's. Here it gets a little bit different because here we want an electron geometry, but we have 2 central atoms. If we have 2 central atoms, we have 2 geometries. So I'm going to call it the carbon geometry and the nitrogen geometry. The one where carbon is the central atom and the one where nitrogen is the central atom. So let's count the domains for carbon. 1, 2, 3 hydrogens and a nitrogen. Total of 4 domains. 4 domains, if you recall, has an electron geometry of tetrahedral. In the case of nitrogen, I have the carbon, 2 hydrogens, and a lone pair. 1, 2, 3, 4 domains. It is also tetrahedral. Now for the electron geometry, or excuse me, for the molecular geometry, it's the same thing. I have 1 for carbon and 1 for nitrogen. Well, in the case of carbon, the 1, 2, 3, 4 domains are all atoms. There's no lone pairs. When that's the case, the electron geometry and the molecular geometry are the same. So this is tetrahedral. In the case of nitrogen, I have 4 domains. One of them is a lone pair. So I use this sheet, 4 domains, 1 lone pair, and we have trigonal pyramid or trigonal pyramidal. So this is trigonal pyramidal. Polar or non-polar. You would probably wouldn't be asked this for an atom with multiple, a molecule with multiple central atoms, but it's polar with respect to nitrogen because for nitrogen you have 2 hydrogens, a carbon, and a lone pair. It's also polar with respect to carbon because you have 2 hydrogens and a nitrogen. So this is polar either way you look at it. Hybrids used. We do not do the hybridization for carbon because, again, it only has an s orbital, so it doesn't hybridize. But we can do it for carbon, and we can do it for nitrogen. So how many domains do we have with respect to carbon? 1, 2, 3, 4. S, P, P, P. sp3. And for nitrogen, 1, 2, 3, 4. Same number of domains, same hybridization. Energetically equivalent resonance forms. It doesn't have a double bond that can move. So no, it doesn't have a double bond at all. Sigma and pi bonds. Let's count the total bonds first. 1, 2, 3, 4, 5, 6. So we have 6 bonds. And in this case, there's no double bonds or no triple bonds, so they're all sigma bonds. So we have 6 sigma and 0 pi. Notice that all of these things that we can find, that we found on this table, are all related to the Lewis structure. And whenever you're asked questions about this, whether it's on ALEX or on an exam or whatever, you need to make sure that you start with the Lewis structure. Starting with the Lewis structure is absolutely essential for figuring out the electron geometry, molecular geometry, polarity, hybrids, energetically equivalent resonance, and sigma and pi bonds. So we need the Lewis structure first, and then we can figure out all of these other factors. And I thought it was very important to show you that these all stem from the Lewis structure.